Hello, thank you for joining me. Tonight I'm going to introduce you to pointers. Now, pointers are important in computer science in general, and they're no less important in C++. Pointers allow you to access the memory of the computer directly, and that's where all the information is stored and manipulated. Tonight I'm going to answer several essential questions. What is a pointer? How do we declare and assign a pointer? Why do we need pointers? What is calling by reference and how does it differ from calling by value? How much space is used by certain types of variables, like booleans, integers, longs, characters? How can we access the address of specific storage locations? After we declare a variable, how can we access its specific address? How do we access the value stored at the address of a pointer? We're going to learn about pointer arithmetic. What happens when we increment a pointer variable or add one to it? What are some specific applications of pointers? And finally, what is the difference between static and dynamic binding? So let's get started. You may recall that a computer is comprised of many memory slots. Each of those slots has a specific address. In this graphic, I've illustrated that with a table of sorts. You'll see on the left in red are a series of addresses. Now these addresses are just hypothetical and they're just used for illustrative purposes only. But in your computer you have a certain number of memory locations. We call this RAM, Random Access Memory. You see that this address block starts at 3240, goes across 10, and then the next row would be 3250, etc. If you were writing a paper in Word, say, on Abraham Lincoln, and you were typing Abraham Lincoln, each of the letters or characters would take up one memory location. Now, we all know that instead of A's or B's, the computer will actually store a number. In fact, it won't store it as a decimal number as illustrated here. It'll store it as a binary number. But you can see the ASCII code for each symbol is stored at a location. When we write a program, we declare variables. In this case, I'm declaring an int called myInt and setting it equal to 23. When you do this, the computer reserves 4 memory locations to store an integer. Notice that the arrow is pointing to the beginning of the storage location, and the myInt variable is preceded with an ampersand. This is how we translate a variable to a variable address. We prepend it with an ampersand. If I declare a character called mychar, it takes up 1 memory location. If we declare a double variable, in this case mydouble, it will take up 8 memory locations. A reasonable question you might ask is, how did I know that an integer will take up 4 memory locations and a double 8? Well, the simple answer is you can find out using C++ code. If you follow this URL, you can see code that I've written to demonstrate that. In it, I'm answering 2 very important questions. How much space is used by certain types of variables? And how can we access the address of that storage? So let's go on over to REPL-IT and take a look at the code. These are your normal includes, and this is the normal namespace declaration. But here I've declared an int, which I'll just simply call A, and a double, which I'll call C, and a boolean, which I'll call D, and a float, which I'll call E. After I've declared those, the computer has set aside memory and remembered the locations of that memory and called those locations respectively A, C, D, and E. Down below here, I've printed out certain values of those variables. For instance, I've called on the C size of method to report the size of the variable A, the size of the variable C, the size of variable D, etc. I've also reported the address by prepending the variable with an ampersand. And then of course I've dumped out the value that we've initialized them up here. So if I run this, you can see that the int takes up 4 spaces, the double 8, the Boolean 1, and the float 4. Now the integer begins its storage at this location. This hexadecimal number indicates its storage location, and of course it has a value of 23. If you look at all these values, they're exactly what we expect them to be. The addresses are normally contiguous. That means the double here will be 4 bytes downstream from the int, and the Boolean will be 8 bytes downstream from the double, and the float will be 1 byte downstream from the Boolean. But that's not always the case, because sometimes with memory management you have gaps, sort of like Swiss cheese, and so you have some locations that are available, some locations that aren't, and so it can be patchy. But a lot of times you can see the pattern of continuous memory locations.